Welcome to my talk on Hilbert-Zait's problem, or the Riemann hypothesis. And in this talk, I want to talk about an idea that I looked at maybe 10 years ago. So I first got interested in the problem, I think, in 2010, when a good friend of mine, Paul Damian, told me about the Riemann hypothesis. And he gave me a paper by Jack Good and Churchhouse. And then from then, that I found a literature on completeness and a paper by Salem in 1953, and we'll talk about that. Talk about that later, and a recent summary of the completeness approach to Hilbert-Zait's problem is given by a nice paper by Balazard. Okay, so let me just quickly begin. There's plenty of YouTube videos talking and explaining the Riemann hypothesis. So just a couple of little asides. Why is it interesting to find the zeros of what's known as the zeta function and its corresponding psi function? Well, if you can characterize the zeros of these functions, essentially Riemann in his classic paper in 1859, his expansion essentially found a formula for the primes. And a lot of people like Gauss, Legendre, Riemann wanted to understand the density of the primes. The formula for the primes depends on Euler's zeta function sitting up here. And Hilbert, maybe one of the most famous mathematicians ever, in 1900 gave a public lecture of 23 problems, and the only problem left that's unresolved is the eighth problem, essentially the Riemann hypothesis. And I've always liked this quote of David Hilbert: if I was to waken after having slept for 1,000 years, my first question would be, has the Riemann hypothesis been proven? And let us just remind ourselves of a couple of classic formulas. So the zeta function is defined as the sum n goes from 1 to infinity of n to the minus s. Defined for real s bigger than 1. We'll have to talk about what's known as analytical continuation. How do we make sense of that function for real s less than or equal to 1? Another formula that you'll see in the slides today, another interesting property, is I can look at the reciprocal zeta function, where mu of n is something called the Mobius function. So that's something that we'll look at as well. And these objects here are sometimes called the Richelieu series, and there's a whole theory of these things. Okay, so the Riemann zeta function, Riemann's famous hypothesis, 1859, and the conjecture is that there's no zeros of zeta of s in the strip 0 to 1. We know that there's no zeros when sigma is bigger than 1. And just very quickly, this idea of analytical continuation, there's something called Ramanujan's master theorem. So under regularity conditions, I can write a function in terms of a Mellin transform as such. And you can see that if I want to make sense of the function at minus s, essentially I just need to know the coefficients in this power series where k is greater than or equal to 0. So if I can make sense of the function for k bigger than 0, I can make sense for negative values of phi as well. And of Hardy, Ramanujan have talked about regularity conditions for the master theorem to hold true. There's an interesting paper by Chowdhury and Kadir around about 2012 that talks about how to apply Ramanujan's master theorem to functions like the zeta function up here, and how it can be used to analytically continue the zeta function to the strip as sigma goes from 0 to 1. And again, Titmarsh, which is a famous book on the theory of the Riemann zeta function has a lot of approaches of integral representations of zeta that it satisfies in the strip 0 to 1. And again, you can get those out of the Ramanujan master theorem. So knowledge of these power series coefficients for k bigger than 0 tells us knowledge about the function at values of minus s. So that's one sort of techniques I like to use for analytical continuation. And remember that I can only really make sense of that sum when real s is bigger than or equal to 1. Oh, and I think the other interesting formula that I'll just put it up here, that zeta at minus 1, if s is minus 1, is essentially the series 1 plus 2 plus 3 plus 4 plus ... And of course, the famous Ramanujan result is that zeta of minus 1 from this analytical continuation that you have down here is minus a 12th. So that's one of the famous formulas that Ramanujan wrote to Hardy about. Okay. Lots of these functions, actually, when you plot them, sort of look quite interesting. So there's a plot of the Riemann zeta function. Lots of people have had a go at trying to characterize all the zeros. I'm not sure what the current research is on characterizing the zeros, but I think the first something like 10 to the power 20 zeros have been calculated by a computer. Turing, rather interestingly, came up with lots of fast computational techniques, so fast computation, to actually calculate the zeta function. And actually he thought that the Riemann hypothesis was wrong. So his idea was just to keep on calculating up all the zeros, and hopefully he would then find one that was off the line, and hence the Riemann hypothesis would be false. So he had a computational approach to try to disprove the Riemann hypothesis. Okay. If I look at the absolute value of the zeta function again, it would look something like this, and it touches the axis at the zeros, and this first zero here is known to be 14.13. And again, remember from Riemann's classic sort of expansion, if I know the zeros, I can essentially find the primes. So it's an interesting way of calculating prime numbers, or finding a duality with primes. One other function that we'll talk about is something called the Mobius function. And again, there's been a lot of work in number theory on the Mobius function. So the Mobius function satisfies the Dirichlet L series, so the reciprocal of the zeta function. And that original Good and Churchhouse paper that Paul gave me was trying to talk about statistical properties of the Mobius function, and given certain properties of the Mobius function, there's an equivalence with the Riemann hypothesis. And lots of people in number theory have studied the behavior of certain properties of the Mobius function, and it's sort of got this random looking behavior. So just to be clear, the Mobius function takes values in the set -1, 0, or 1. Every number has a prime factorization. So if there's a square in the prime factorization, the Mobius function is equal to 0. And if there's an even number of prime factors, it's equal to 1. And if it's got an odd number of prime factors, it's equal to -1. So essentially you look at the prime factorization of a number. If it's square free, it'll either be -1 or 1. If it's got a square, it'll be 0. So it's sort of an interesting function, and satisfies the fact that the reciprocal zeta function is the sum of Mobius function over n to the -s. And a lot of insights into primes can also be deduced from this Mobius function, its behavior. But the difficulty is in actually assessing the behavior of the Mobius function because of its so not easy to figure out. Okay, so here was my approach back in 2011. So I want to talk about completeness of a family of probability distributions. And the original paper, it's only like a 2-page paper, by Salem in 1953 came up with an equivalent completeness condition for the Riemann hypothesis. And a more recent paper by Moll et al. 2010 on something called the Cauchy-Smolich transformation also has similar identities as well. And if you look in the Salem paper, he shows how you can interchange integrals and sums and find these identities. So essentially, this is a slight modification of the Salem result. If I look at, so Salem starts with this identity here. If I regularize the zeta function by 1 minus 2 to the 1 minus s, I get the sum of, as n goes from 1 to infinity, of minus 1 to the n plus 1 n to the minus s. And then if I slightly adjust by a half and work out something called the Dirichlet beta L function, I can essentially interchange integral and summation again. Look at the Salem paper for the Fubini regularity conditions, and essentially I can prove that if I've got this regularized version of the zeta function, I end up essentially with a Mellin transform of this probability distribution. So this is called the hyperbolic secant distribution. And with the, I will call this the power tilted hyperbolic secant distribution. And of course I can take this Mellin transform and make it into a Fourier transform by transforming, by exponentiating x equals e to the minus y, for example. And so the interesting insight is I can try and obtain a contradiction, right? This formula holds true for real s greater than 0. Now we know that the zeta function has zeros on the line real s equals a half. The question is, does it have any zeros on the line from a half to 1? So we could suppose by contradiction that the zeta function was 0 for sigma between a half and 1, and so that would make all these integrals here equal to 0. And then essentially the Riemann hypothesis would be equivalent to what's known as the completeness of the power tilted hyperbolic secant distribution in the region where sigma goes from a half to 1. Actually, there's so let me talk about that. So there's our idea. Suppose for a contradiction that the zeta function is equal to 0. Again, let's just restrict ourselves to the critical strip from a half to 1. And then essentially from our Salem formula here, I know that all these integrals are 0. I can transform x to any constant times x. So I can go up here, and I can also add any weights. So, suppose for a contradiction that zeta of 0 is equal to, that the psi function is equal to 0 in some part off the critical line, essentially I'll get a set of inequalities. I get an inequality that looks like this. Now, the tricky or interesting bit of these completeness results is how do I choose my weights Wn? And there's a very nice identity, and we'll talk about it on the next slide as well, that takes the exponential function and replaces it by a weighted sum of these secant functions. And again, there's our favorite Mobius function. So maybe this is a completeness probabilistic probability density version of how the Mobius function comes into the Riemann hypothesis. Now, why is that useful? Well, there's something called Lurker's theorem. And Widder in the 1940s has a book that talks about Lurker's theorem. What does Lurker's theorem say? Well, if the integral of e to the minus theta x times the probability density is equal to 0 for all theta, then that implies that p of x must be equal to 0 almost everywhere. So Lurker's theorem is about the exponential function. We would like to know what are the conditions for if I take the secant So if that's equal to 0 for all theta, does that imply that P of x is equal to 0? So that's essentially what we mean by a completeness result. And then, so a sufficient condition is if P of x integrates 1 upon x at the origin. So this is a rather interesting result. We know completeness of the exponential function. You'll see in a minute we know completeness of the hyperbolic secant function as long as P of x integrates 1 upon x at the origin. And this is an interesting result by Lai and David Veer-Jones, I think around about 1978. And that's interesting from a statistical point of view. It's been well known that distributions in something called the exponential family, I think Ollie Bandhoff-Nielsen in the 1960s showed that the exponential family of probability distributions is complete. And essentially this Lai and Veer-Jones paper shows under certain regularity conditions when the hyperbolic secant distribution is complete. Now in our case we also have the power tilted version of the hyperbolic sequence. So remember that we also have to add in an extra term x to the sigma minus 1, where sigma is greater than a half. Okay, so that's the idea of completeness. Suppose for a contradiction it's got a 0 off the line, then we know that we've got this big sum of integrals must be equal to 0. And then we know essentially, or we're trying to get back to Lercher's theorem to prove completeness, we know that if we pick the weights to be minus 1 to the n times the Mobius function at 2n plus 1, we know we're going to get back to the exponential function, and then Lercher's theorem will give us our contradiction. So that's the basic idea. And again, this is an interesting probabilistic fact that's related to completeness in the Riemann hypothesis. So I think these two identities are sort of important to know. So from the Salem result, we know that the zeta function is essentially a Mellin transform of this hyperbolic secant function. And we know from the previous slide that the exponential can be written as a sum of secants. And then, of course, we know we have the other way around as two. So this is one of these nice sort of statistical, functional analysis dualities. We can write the exponential function as a sum of secants, and we can write the secant as a sum of exponentials. So rather interesting dualities. And again, the proof of this, if you looked in the Lai and David Veer-Jones paper, you could figure out the proof. So you have to basically solve out these linear systems of equations. You find a little identity or recursion that the weights have to satisfy, and essentially the solution to that is our good old friend, the Mobius function. So another interpretation of the Mobius function. Okay, so how would we obtain a contradiction? So there's a nice paper by Levinson in the 1970s that looks at this. And so the insight I had here, 10 years ago, was essentially let's approximate the gamma function. And we know that the gamma function has no zeros. So if we can find a lower bound and an upper bound, we essentially know the fact that the gamma function is not 0. So essentially we'll be able to obtain a contradiction to essentially if the zeta function has a 0 off the line. So if the zeta function does have a 0 from a half to 1, then we know that this sum is equal to 0, and essentially we find a contradiction. So remember that under our supposing for a contradiction that the zeta function is equal to 0, we know that this sum of terms here is equal to 0. So I can try and use it to approximate the gamma function. So, and again, we've also got that very nice, if I go back, this very nice sort of approximation completeness identities, I can approximate the exponential by a sum of secants and vice versa. So essentially, I can replace the exponential by its sum of secants, and essentially now I have a tail term. And again, if I do a bunch of simple algebra, essentially what we're interested in is this integral here. And of course, the difficulty will be, so the difference between these two is one has the Mobius function and one does not. It'll be easy to understand our function phi sub n, but it'll be slightly harder to understand the bit with the Mobius function. And essentially it's because I want to be able to do a Fubini type interchange of sum and integral. Another sort of basic factors, the secant function is decreasing in k, just definitional. Let a sub k be the secant tilted by the exponential. And now there's a very cute little inequality that I've always liked of Bellman's, one of my favorite mathematicians. If I have a decreasing sequence of terms, we have the alternating sign inequality. And why is that useful? Because, well, essentially, I want to prove that error term tends to zero. And let me just remind you that this error term doesn't have the Mobius function in, the gamma function does. So this is a rather simple application, but a cute application of Bellman's alternating sign inequality. Well, now I want to have like a lower bound and an upper bound, so I know that this error term will be tending to zero. And as with all of these problems, the devil is in the details. So hopefully with a little bit of work and a little bit of bounding, I can find a constant k such that this sequence here is decreasing. Remember that there's always an issue with the behavior of the Mobius function. So even though we know that the absolute value of the Mobius function is equal to 1, remember it only takes values minus 1, 0, 1, it's still quite hard to basically bound these series and to allow us to do a Fubini type result. Okay, so devil in the details with these boundings. Again, if I now look at the norm of the gamma function, some devil in the details sitting here. One inequality that's worth noting, and this is what you can use to show the hyperbolic secant version of the completeness result, is that the sum of secants is basically order 1 upon x at the origin. Maybe that bound can be improved, and again that's what led us to the condition that you need that integral of p of x over x being less than infinity for the, or at least that's a sufficient condition to be true. And again, given that I've bounded the gamma function on both sides, and given that I know that error term tends to 0, and given I know that the gamma function doesn't have any zeros, essentially that sort of sandwich inequality would obtain a contradiction. So as I said, devil in the details for checking to see whether you can bound these things to 0 in the strip when sigma goes from 1/2 to 1. But I think you get the idea that the completeness approach to the Riemann hypothesis is sort of an interesting one. Let me just sort of summarize. The idea is to show that by contradiction, that Zeta function couldn't have any zeros off the line. The key identity was essentially Salem's identity, and the key distribution that you have to look at completeness of is the what I call the power-tilted hyperbolic secant distribution. And again, remember, there's that one of the key things in the proof is that there are weights that switch you between the exponential function and the secant function, and again, it would be an application of Lurker's theorem. And again, one approach to finding contradictions in these completeness things is to try and approximate the gamma function and get inequality bounds on either side. Anyway, thank you for listening. Another possible approach to looking at the Riemann hypothesis, and an interesting duality between, or an equivalence of the Riemann hypothesis to completeness of probability families of distributions. Thank you for listening.